l'Aleph. Seguì le sue ridicole istruzioni e finalmente se ne andò. Chiuse cautamente la botola. L'oscurità, nonostante una fessura che in seguito distinsi, mi parve totale. Improvvisamente compresi il pericolo che correvo. Mi ero lasciato sotterrare da un pazzo dopo aver bevuto un veleno. Le bravate di Carlos svelavano l'intima paura che io non vedessi il prodigio. Carlos, per difendere il suo delirio, per non sapere che era pazzo, doveva uccidermi. Sentii un confuso malessere che volli attribuire alla rigidità, non all'effetto di un narcotico. Chiusi gli occhi, li riaprii. E allora vidi l'Aleph. E arrivo ora all'ineffabile centro del mio racconto e comincia qui la mia disperazione di scrittore. Ogni linguaggio è un alfabeto di simboli il cui uso presuppone un passato che gli interlocutori condividono. Come trasmettere agli altri l'infinito Aleph che la mia timorosa memoria a stento abbraccia? I mistici, in simili circostanze, sono prodighi di emblemi per significare la divinità. Un persiano parla di un uccello che in qualche modo è tutti gli uccelli. Alanus de insulis, di una sfera il cui centro è dappertutto e la circonferenza in nessun luogo. Ezechiele di un angelo con 4 volti che si dirige contemporaneamente a oriente, a occidente, a nord e a sud. E non invano io ricordo codeste inconcepibili analogie. Esse hanno una qualche relazione con l'Aleph. Forse gli dei non mi negherebbero la scoperta di un'immagine equivalente, ma questa relazione resterebbe contaminata di letteratura, di falsità. D'altronde il problema centrale è insolubile. L'enumerazione, sia pure parziale, di un insieme infinito. In quell'istante gigantesco ho visto milioni di atti gradevoli o atroci. Nessuno di essi mi stupì quanto il fatto che tutti occupassero lo stesso punto, senza sovrapposizione e senza trasparenza. Quel che videro i miei occhi fu simultaneo. Ciò che trascriverò successivo, perché tale è il linguaggio. Qualcosa tuttavia io annoterò. Nella parte inferiore della scala sulla destra vidi una piccola sfera cangiante di quasi intollerabile fulgore. Dapprima credetti ruotasse, poi compresi che quel movimento era un'illusione prodotta dai vertiginosi spettacoli che essa racchiudeva. Il diametro dell'Aleph sarà stato di 2 o 3 centimetri, ma lo spazio cosmico vi era contenuto senza che la vastità ne soffrisse. Ogni cosa, il cristallo dello specchio ad esempio, era infinite cose perché io la vedevo distintamente da tutti i punti dell'universo. Vidi il popoloso mare, vidi l'alba e la sera, vidi le moltitudini d'America, vidi un'argentea ragnatela al centro di una nera piramide, vidi un labirinto spezzato, era Londra. Vidi infiniti occhi vicini che si fissavano in me come in uno specchio. Vidi tutti gli specchi del pianeta e nessuno mi rifletté. E vidi in un cortile interno di Calle Soler le stesse mattonelle che 30 anni prima avevo viste nell'andito di una casa di Fray Bentos. Vidi grappoli, neve, tabacco, vene di metallo, vapor d'acqua. Vidi convessi deserti equatoriali e ciascuno dei loro granelli di sabbia. vidi Inverness, una donna che non dimenticherò mai. Vidi la violenta chioma, l'altero corpo, vidi un tumore nel petto. Vidi un cerchio di terra secca in un sentiero dove prima era un albero. Vidi, in una casa di Adrogué, un esemplare della prima versione inglese di Plinio, quella di Philemon Holland. Vidi contemporaneamente ogni lettera di ogni pagina. E da bambino io solevo meravigliarmi del fatto che le lettere di un volume chiuso non si mescolassero e perdessero durante la notte. Vidi insieme il giorno e la notte di quel giorno. Vidi un tramonto a Querétaro che sembrava riflettere il colore di una rosa del Bengala. Vidi la mia stanza da letto vuota. Vidi in un gabinetto di Alkmaar un globo terracqueo posto tra due specchi che lo moltiplicano senza fine. Vidi cavalli con la criniera al vento su una spiaggia del Mar Caspio. Vidi la delicata ossatura di una mano. Vidi i sopravvissuti a una battaglia in atto di mandare cartoline. Vidi in una vetrina di Mirzapur un mazzo di carte spagnolo. Vidi le ombre oblique di alcune felci sul pavimento di una serra. Vidi tigri, stantuffi, bisonti, mariciate, eserciti. Vidi tutte le formiche che esistono sulla terra. Vidi un astrolabio persiano e vidi in un cassetto della scrivania, e la calligrafia mi fece tremare, lettere oscene, incredibili, precise, che Beatriz aveva scritto a Carlos Argentino. Vidi una dorata tomba alla Chacarita, vidi i resti atroci di quanto deliziosamente era stata Beatriz Viterbo. Vidi la circolazione del mio oscuro sangue, vidi il meccanismo dell'amore e la modificazione della morte. Vidi l'Alef, vidi l'Alef, da tutti i punti. Vidi nell'Alef la terra e nella terra di nuovo l'Alef e nell'Alef la terra. Vidi il mio volto, le mie viscere. Vidi il tuo volto e provai vertigine e piansi, perché i miei occhi avevano visto l'oggetto segreto e supposto, il cui nome usurpano gli uomini, ma che nessun uomo ha contemplato, l'inconcepibile universo.
Umberto Petrin, dov'è? Torna pure su, e Stefano Benni.
Umberto Petrin and Stefano Benni.
Le ringraziamo.
We want to thank you.
Buonasera, macchine per
good
scoprire
evening.
dal
So,
bosone di Higgs alla nuova
machines
fisica.
to discover from Higgs boson to new physics. So let us start right now. I'd like to ask Fabiola Giannotti and Fernando Ferroni to come here and have a seat.
Eravamo fatti tutta una scaletta.
We had prepared kind of an outline, but we decided we're not going to follow our outline. Fabiola, you are well known for a number of reasons, also in the media. You are the Director General of CERN. The first question which came to our mind, many of you are physicists, so we need to stick to a plain language. Even though we shall try to be quite specific. Why do we need equipment and devices which are so big to investigate things and objects which are so small? In order to study in detail components which are very small, components of matter. We try to understand how the fundamental constituents work of protons and electrons, quarks, which are the fundamental elements of atoms. We need a lot of energy. These accelerators can be regarded as huge microscopes, allowing us not so much to study cells, but rather to study the major components of the matter at scales of 1/10000000th of a meter. In order to study this very small dimension, we need huge energies. So in order to generate great energies, we need great accelerators. So maybe one day, with the development of technology, we will manage to have more compact, smaller accelerators. But in order to generate huge energies, now we need very big machines. Fermi had forecast accelerators of huge size. Fermi had foreseen the need for energies, what we have achieved with LHC. 27 kilometers. Fermi, at the time, had no other solution but thinking of putting an accelerator orbiting around the Earth, and that accelerator would reach the energy that the LHC is achieving today. If I can keep talking about this theme, Fermi shows that we should never give up, because at the time, no one following Fermi, who had foreseen such an accelerator, would have never thought of achieving that. But we did that with the LHC, and we invented two very important things. Colliding beams, one beam against another beam. At the time, accelerators were a beam against a fixed target. And the superconductor magnets. So the ideas and the ingenuousness and curiosity of man allows us to take a very big stride forward, huge leaps forward. So talking about LHC, in the video that we were watching in the beginning, we saw this growth in terms of dimension, starting from the 70s. So it's a huge achievement. It's titanic achievement. But can we say something more about the story of LHC? The early discussions about the chance to build a big collider of protons in the tunnel, in the existing tunnel that had housed that machine, which is called the LEP, the previous machine. This took place in mid-80s. LHC started operating in 2010. So 25 years between the first ideas and the actual operation. But previous physicists in the 70s, when the LEP tunnel was built, in their vision, they were thinking of the future. They were thinking of a hadron collider with protons. So they built that tunnel with a radius which was bigger than necessary, figuring out already the future machine. So in this 25 years of history of LHC, from the very first ideas to the operation, these 25 years were wonderful, but very, very tough, very hard. We knew that we were building tools such as an accelerator and detectors for experiments that were unprecedented, practically almost impossible at the time, with technologies that at the time did not exist. So those years have been ideas where we brought up ideas, and we were very stubborn, determined. There were major problems when we work at the edge of technology. If you shift this, if you move something, I mean, it's very difficult. So it required courage, stubbornness. We had to take a step forward, sometimes also some step backwards, and in the end we managed. Talking about this technology aspect, when you were approaching the time of crucial experiments, I think we can talk about this briefly. Some fear arose around this experiment. There was this black hole. It is difficult to convince anyone that a particle accelerator having energy apparently never achieved before can not be dangerous, but if information are disseminated properly, this can be done. Even though LHC is a very powerful piece of device, a machine with 13 billions of electron volts, nature provides particles falling down from the sky, interacting with air, having much higher energies and generating interactions at higher energy. So if the black hole had to be produced, we would have the black hole already, so we wouldn't be here telling the story. But I'm here, I'm telling the story, so actually creating a black hole is not so easy. We also have other stories about the gravitational waves. Actually, we were saying that there is this fascination in the media with the physics. I'm a researcher in a different field, but the scientific culture in Italy has been neglected, not so much that concerning physics. There is a actually, we need to combine science and humanities, and this is quite positive. The role of fear about experiments that results into attitudes which can which go against a scientific attitude. What could we do in order to disseminate these topics better? Awareness. We can say that in our world, over the last 20 years, there was a greater awareness. The need to explain in a simple but rigorous manner what we were doing, why we were doing that, what we thought we could achieve, and what could be the potential fallbacks on society. I think that this was a fundamental element of the media success of physics. I think that this community actually realized this potential before other sciences. There's an example, which maybe it's a bit too simple. Medicine is a very easy ground for dissemination. People are scared to die, so people are scared to become ill. So there's this need to understand, which is very strong. But also in the world of medicine, sometimes there are swindles because people talk about things which are not really true. But going back to physics, this science, even though there were discoveries which were not so important, actually we had more important discoveries in the last 6 or 7 years, but there was this need for communication that was developing. So I think that we have not yet reached the point where we are bound, where we want to be, but the community has become aware of this need, and now we are equipped with the necessary tools for communication. Major scientists, great scientists, were not actually communicators. But, as is well known, this is the most famous Albert Einstein. It appears that when he communicated, there were big masses of people listening to him. I fully agree with what Nando pointed out. It's really important to communicate for a number of reasons. First of all, knowledge belongs to everyone. What we do, we try to advance knowledge. And this belongs to the whole mankind. I like to make comparison with the art. I mean, when a painter actually creates a work of art, he doesn't want to keep that work of art at home. He wants to expose it, to exhibit this work of art to the audience. So what we do belongs to all the human beings. But then we work in research, in labs, which are sponsored, which are funded through public money. So it's important to communicate what we do, but in an accessible manner. The role of ultra-technology detectors is fundamental to actually discover the basis of the universe. So let's have a look at this video, and then we shall go back to our discussion. We, the planets and stars and galaxies, we are all made of matter, which is just a small part of what exists in the universe. We represent just 4% of everything. 1/4 of the universe, 26%, is of an invisible matter. We don't know what it is made of, and we call it dark matter. The remaining part of the universe is made of a component which is as mysterious, which is called dark energy. Dark matter does not interact but weakly with ordinary matter, but its effects are felt through gravity. So last century it was possible to figure out that it existed. Observing galaxies, we see something surprising, amazing. According to Kepler's law, the outermost stars should revolve more slowly than the innermost ones. But it is amazing, they revolve at the same speed. The cause of this phenomenon is this gravity, which is exercised by something invisible. This invisible thing is dark matter, a sort of cloud, a bigger halo than galaxies themselves. There's another way to identify the presence of dark matter. Let's imagine an eye receiving the light coming from a galaxy. Let's imagine that between the eye and the galaxy there is a mass of dark matter, so the light will be deflected in this way. And in that way, since we are in a 3D space, images form a disk, a ring. This is called the Einstein's ring, the gravitational lens, another sign of the existence of the dark matter. Scientists are actually chasing dark matter, for instance, through equipment in the cosmic silence of underground labs, or through experimental activities in space and the space stations. Sooner or later we shall understand what it is made of.
Beh, anche questi strumenti hanno un senso, effettivamente.
Well, this equipment makes sense, of course. But let's go back to what we were talking about accelerators. And also the media success. Well, journalists helped somehow. Well, of course, correct me if I'm wrong.
Forse per voi impropria, ma di grande successo mediatico di particelle di Dio o cose di questo genere.
God's particle was actually a definition given by a journalist. Maybe that's not so effective to you, but that's what they use as a definition for the Higgs boson. Well, without prejudice to the fact that it can be something that really makes sense. It's just like the water bomb that was used to identify the storms last summer, but it had some media effect and was actually devised by a journalist. We just watched the video, but here we hear about the Higgs boson, and the accelerators have found this last piece of the jigsaw. People think that this is the last piece of the jigsaw. Maybe it's just the first one. How does it work? Well, it's definitely a piece of our knowledge, the last piece of our knowledge. Over the past 50 years, we have developed a very complex theory, which is commonly referred to as the standard model, the weak electromagnetic interactions, basically. And just like building blocks, they are all small pieces that were discovered one after the other, and they were placed in the right place. And this building could actually stand if the Higgs boson existed, if it had some properties, which are the ones that we have found through our equipment. So it is basically the backbone that keeps the whole building standing. So the Higgs boson is the point of arrival of this theory. Of course, if this opens new doors for future opportunities, we still don't know. But what the video has shown is that even if that building were complete, it would be anyway 4% of the history of the universe. So there's 96% left. So I think we need to explore other places if we want to enhance our knowledge. So it would be limiting to say that that's enough to explain. Yes, it explains a very small part. And luckily, we still have 96% of the universe to explore. The path to knowledge is very long, and it's great to have this big challenge ahead of us, a challenge we can rise up to understand how's the universe and what's the universe made of. The video talks about the dark matter. We are trying to chase this dark matter with two pieces of equipment, the underground detectors that we have seen in the video, or the orbital station, the MIS mission, or the LHC as well. They could tell us something important about the dark matter, because if the dark matter is made up of heavy particles with a weak interaction, we might be able to produce them with the Large Hadron Collider over the next few years. We will go back to this, but it's just like saying, well, you expect that, is this part of a strategy, or is something you find out, well, not by accident really, but something that is a sort of collateral damage of your discoveries. Well, the LHC was built, like many other instruments, to address a number of open questions. And when it was built, one of the major issues to explore was the origin of mass and particles, and the Higgs boson is related to that. Dark matter was in the list of our open questions, but the LHC is not the only instrument. And with the LHC only, we won't be able to answer all the fundamental open questions in physics and understand the 95% of the dark universe. So we need several approaches. One is not enough. So we are trying to approach the problem from different standpoints and with different instruments. So we are chasing the dark matter with all the instruments, with all the equipment that technology makes available, that human ingenuity makes available, and that people have invented over the years. So before saying goodbye, I have a last question about the Italian role, not with respect to the building of this equipment and technology, but, you know, the brains that are involved. Well, there's no question about the brains that are involved. Joking aside. Well, Italy is the founding partner. Well, Caldomaggi was one of the persons that actually had the idea of setting up CERN. So Italy has been involved in this undertaking since the very beginning. It's been 60 years. We've gone down a long path. So the problem back then was trying to put back the pieces to compete with the Americans that had everything. Well, today the Americans come to work to CERN. It's their biggest laboratory to bear witness to the success of this initiative. So Italy has always participated in all the experiments that were carried out at CERN with its expertise, with the funds, with the research of the INFS. I'm not talking about money here, I'm not talking about resources, but we invested lots of energy, not only in terms of young people, young brains, as we call them, that spent some 20 years to cross this desert. And they finally had a chance to see Higgs boson. But there was a deep involvement on the part of the Italian industry, if possible. I think that the INFN is a protagonist of this phenomenon. There's top-notch technology available in our industry. From a mechanical standpoint, so this is a distinctive feature of our industry, which is a leader in the world. The director of Fermilab Laboratories came to the ministry a few days ago. He was asking for help to build the superconductive accelerating component of their accelerator. So I think this is evidence of our role. And CERN is teeming with young Italians, so I think the official language in CERN's cafeteria is Italian. And I'm sure Fabiola can say much more about their contribution. Well, in my current position, but also previously when I was coordinating one of the large experiments, I had a chance to meet many people over the world. And Italians are second to none. We have trained very young, very good young people, and hopefully they will stay with us for the future. They are really an asset for our country. Thank you.
Attenzione al gradino.
Mind the step.
E ora diamo tempo di prepararsi a Umberto Bedrin e Stefano
Benni. We're waiting for Umberto Bedrin and Stefano Benni, who are going to reach us here on the stage in the next minute.
Raymond Queneau, il breve finale di Piccola cosmogonia portatile. Le gambe del battello, del vapore al soffio, s'arrotondano e si intrecciano e diventano un'elica. I lettori e lettori s'attiran della rana la forza elettrica ove galvanizzano fino a che ne raggiungono la folgare, mentre che certe braccia su dall'alto di Saint-Sulpice vanno diffondendo senza fili le bubbole e gli imbrogli destinati agli ingenui. Dan le onde un sistema nervoso alla meccanica. Le luminose dentro l'obiettivo si infilano e pennello e pennellessa sfidano nel ritratto identitivo. La pompa si spolmona e su stampelle di rotarie l'iperione lanciasi degli equini. Vapore che cosparge l'occhio ai vitelli di scintille pazze di carbone e che dà un punto fino all'altro al viaggiatore da vela. Ecco, officine nascer come funghi e vedi pure la crittogamia e il proliferare di turbine, motori, marchingegni nei travagli del parto come una partenogenesi di macchine che sono concepite da un'idea e quindi partoriscono un'azione. Il gas che viene prodotto dal carbon si profuma di colori d'arcobaleno e questo per nutrire tutto un mondo qu'odora di astrazione, ma che fresa e che lamina, inchioda e lime a vita al par d'una mamma gigogne per generare tanti oggetti ben reali, al par del cacciavite, della capsula e pur delle tenaglie dell'auto, bicicletta e altrettanto della chincaglieria, del camion, del sottomarin, dell'accumulatore, del fermaglio a spirale, del colino ferro da stiro e del ventilatore d'artiglieria a proiettile e pur anco del cavatappi e così del bulldozer, draga, revolver, radiatore, la radio e del pari l'automatica lavatrice e aggiungi il frigorifero. L'infinita marmaglia delle astuzie casalinghe, dei mezzi di trasporto, utensili, nonché gadgets esposti nella fiera di Le Pont della grande industria. Del selenio, l'occhio s'apre e la porta fa il medesimo. Se scendono gradi, tu senti il termostato sospirare. Hanno certo iniziativa le velocità messe lì in scatola e le due tartarughe rotolanti per le forze attrattive vanno e vengono e così pur per forze repulsive. Nel frattempo del calcolo i sauriani si insiduan poderosi fracassando tavole logaritmiche, le regole, gli abachi e le loro madri macchine setacciatrici e i padri binari, l'elettronico zio dall'aquilino sguardo ammirano spaventati questi modesti atleti, i quali polverizzano i record stabiliti da quei bipedi che pure san contare, san parlare e curare i sauriani del calcolo e i bipedi che pure san contare, parlare, Curare san del calcolo i sauriani e i bipedi che pure san contare, parlare, contare, parlare, nonché parlare, contare, 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 curare, 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 parlare, parlare, parlare dei sauriani, del calcolo e ancora parlare, parlare.
Approfittiamo per salutare Stefano Benni
We'll take the opportunity to
e Umberto Pedrin ancora,
say hello to Stefano
che
Benni
troviamo anche più
and Umberto
tardi.
Petrin. We'll
Grazie.
meet them later. Thank you.
Adesso ci rimettiamo a parlare di
Now,
fisica, ma in realtà lo
let's
stiamo
go back talking about physics. We were still doing it, actually.
Michelangelo
I
Mangano,
would like to
Guido
invite
Tonelli.
Michelangelo Mangano and Guido Tonelli here to the stage, please.
Bene, allora, fisico teorico del CERN. Io quando leggo fisico teorico,
Theoretical physicists. Well, I'm a geologist, so, you know,
Guido Tonelli,
Guido Tonelli,
Università di Pisa,
University of Pisa. We met once in a fascinating seminar I was attending, and I also stole some pictures from there, but anyway, I didn't steal anything actually, because the credits were there. So let's go into the details of the machines and discovery as well. I will ask you the same question I asked before. Is there a work plan for what you are planning to discover? Or is it something that happens by accident, a sort of serendipity? Well, there are phases. There are phases in research. There are phases in experiments. There are phenomena that are poorly understood or not clearly understood. We have to set forth theories, and we set forth more theories, and we have to understand which of them is correct. So we have different expectations of different theories, so we carry out experiments to verify the expectations we have for individual theories. But when we have so much to explore, and the question is for both of you, I think any direction is good, isn't it? Well, actually not, because one of the things we have learned over the past 50 years is that even if what surrounds us manifests itself in so many different forms, we've got light, we've got a storm, we've got the sun, we've got the phenomena that we observe in a laboratory environment. Very few laws can be written down on a piece of paper to describe basically everything. So there are extremely strong constraints to the flexibility that we have in setting forth new theories. So, within these constraints, the prediction values of theories, they go beyond what we already know, beyond the standard model. It's not easy to plan. A correct path is that of exploring the smallest thing, because starting from the smallest thing, we can build the biggest thing. So a clear direction is that of going towards higher energies to explore smaller ones. There are phases in which there's a precise goal. The discovery of the Higgs boson has closed a phase that lasted over 40 years to improve our knowledge of the standard model. Now we have a new phase. We don't have some landmarks like the Higgs boson. We are not totally in the dark, of course. We've got some ideas, and it is very likely that discoveries will be different. Landmarks are necessary to guide us in a given direction, and along the journey we might find something different than what we expect. Well, the phase we are going through is wonderful on some levels, because we have discovered this missing piece of the Standard Model, so the Higgs Boson. So we understood some of the crucial phases of the history of the universe and the structure of our universe. We are somehow celebrating the triumph of a theory that was set forth over the past 50 years. And the open questions you have listed, the list of the open questions is embarrassing for physicists, because we know nothing of the dark matter, we know nothing of the mechanism that produced changes in fluctuations of the universe that led to the universe. We know nothing of the matter-antimatter asymmetry. What happens to antimatter? We can't answer this question. We know nothing of the dark energy. This acceleration that apparently is driving everything apart from everything indefinitely. So the lack of knowledge of physicists and scientists in general is huge. So right now, in a moment when we have a theory that is actually working, we realize that none of these problems is actually explained in this theory. So research, a new accelerator, will be useful to challenge this theory, to break this theory somewhere or somehow, maybe going in unexpected directions. And starting from that challenge, starting from that crisis, a more complete and exhaustive theory will be set forward, which will include the Standard Model as a peculiar low-energy case. And it's really difficult to think about a more exciting moment for physics. You're always looking for this smallest things. They have to explain the biggest things. How small should this thing be? I'm impressed when I hear about this. How small? Well, exploring small dimensions means exploring large energies, big energies. We know that our world, we are of a given height, we live X number of years, so we have very clear spatial and temporal dimensions. As soon as you take some distance from this, things change, and quantum mechanics and other disciplines were born out of this. So when you explore what is incredibly small, you have to set aside all your certainties. After 100 years, we are still having difficulties in understanding quantum mechanics and relativity fully, things that were actually produced 100 years ago. So if we manage to explore dimensions that are even smaller, there could be surprises. There are some scholars that believe that we might open dimensions that were developed in a primordial universe and they're closed again in the cold and old universe in which we are currently living. And if we opened new dimensions, we might think of a world that is not four-dimensional, but maybe has 6, 12 dimensions. So maybe we might understand gravity. Then one of the most mysterious things, the most common force we're all familiar with. Think about what it might mean in terms of our vision of the world, saying that we have understood that our universe develops over several dimensions. So it will be an epoch-making moment, an epoch-making theory of how we conceive the universe of matter. Would you like to add something? Well, the question of gravity is really important because it gives us a scale, it gives us a landmark. Well, how small was your question? And I can give you a very accurate answer to this. Gravitational forces between two protons have to be compared to the electrical force, for example, between two protons. That's a scale we're referring to in terms of size. It is characterized by energy or distance and corresponds to a factor of 1,000,000 billions plus the energy of the LHC. So we know that if we reached that level of energy, we would find out that the space-time has some quantum characteristics, and that would be a breaking point with our idea of space and time. The phenomena Guido was referring to are actually related to this. the world might be way more different than what we expect. We might have many more dimensions. And this, of course, would imply that there are energies that are closer to us. And we might be able even to observe these phenomena. But if this didn't happen, the Planck scale would be a unit of measurement for our knowledge. To have some discoveries have to be guaranteed. So we are bordering on philosophy here. Just to go back to your experiment CMS, could you briefly talk about this so we can move on to the video that will talk about how the accelerators have developed? Well, the big quest for the Higgs boson was carried out with two experiments. They were actually competing and collaborating at one time. Something magical made it possible for Fabiola and I to direct the two experiments. Two Italians were actually leading these two experiments, and it was very unusual, very peculiar. And these two experiments reached the finish line at the same time. To find the particles we had looked for so long. There are billions of scientists, thousands of scientists, and the two experiments compete with different technology. And this is a guarantee with respect to the scientific results, because we are looking for very rare phenomena. Particles are very elusive. So having two different technologies and having different software, different people, means being extremely sure that the results might be checked, mutual results might be checked. And so we know that we might be able to announce to the world that we have found a new stage of matter. This is a very careful attitude. We always have to have our scientists. So let's watch the video. Well, physicists are very good. Elusive particles. That's fantastic. A particle with personality, she doesn't want to be found. Something fantastic, great. I love it. Let's watch the video.
This year's prize is about something very small that makes all the difference.
At CERN's foundation in 1954, the world of particle physics was a very different one. Scientists were trying to come to grips with the plethora of particles observed in nature. They lacked an overall framework to explain these basic constituents of matter and the forces that act upon them. This framework would later become known as the Standard Model. By the end of the decade, CERN physicists were already providing insights into the weak interaction, a force without which the sun would not shine. The 1960s saw the birth of electroweak theory, which unifies the weak and electromagnetic forces. A vital part of this is a mechanism that accounts for the vastly different ranges of these forces, as well as for particle masses. These were beautiful concepts, but they needed experimental evidence to back them up. Particle physicists embarked on a global search for the carriers of the weak force, W and Z bosons, whose existence would prove the theorists right. In 1976, CERN brought the SPS on stream. Larger and more powerful than CERN's previous accelerators, the SPS would go on to collide protons with antiprotons. By 1983, SPS experiments had seen W and Z bosons. Their long-awaited discovery led to the Nobel Prize for CERN's Carlo Rubbia and Simon van der Meer.
The discovery of the W and Z is not the end. It is the beginning.
The next step began when LEP, the 27-kilometer Large Electron-Positron Collider, was switched on in 1989. It was designed to study weak bosons in detail. The LEP collaborations soon had their first major result. By measuring the decays of Z bosons, they found that nature has 3 and only 3 families of matter particles. Everything we see in the universe is made of the lightest family. During its 11 years of operation, LEP placed electroweak theory on solid experimental ground. The Standard Model was almost complete, but what accounted for the mass of particles? But there was one last missing piece of the puzzle to uncover, the physical manifestation of the Brout-Englert-Higgs mechanism, a particle called the Higgs boson. Its discovery was in sight. With the construction of the Large Hadron Collider, CERN would take its first steps into a new century of discovery.
Today is a special day.
On the 4th of July 2012, the CMS and ATLAS collaborations announced the discovery of Higgs bosons.
These results are the outcome of the ingenuity, vision, and painstaking work of our community, from accelerator to detector, instrumentation, computing, and physics.
We have observed a new boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviations.
It was the final evidence the world had been waiting for, hitting headlines around the world, winning the Nobel Prize for Peter Higgs and François Englert, and cementing CERN's pivotal role in the development of the Standard Model. The Higgs boson completes the Standard Model, but many questions about our universe remain unanswered. Mysteries that will captivate future generations of scientists and lead them to untold discoveries.
We had agreed upon a few questions, and we shall try to ask them more briefly as to the risks and difficulties and the certainty that the ground has to be a ground of exploration and research. There's something which comes to my mind watching this video as a non-physicist, so I try to interpret the audience's standpoint. We are surprised, those who are not insiders. We try to understand that. When the particle takes mass, doesn't it have mass already? Aren't we all a sort of perturbation of the field? But this is difficult to accept. Particles have mass. They don't take mass. They have mass. When people say they take mass, this is incorrect. When a particle is created, it is created on its mass. It is created with a mass because it is created in an environment, our universe. So the instant it is produced, it has to interact with the universe. More specifically, it has to interact with this Higgs field, which permeates the universe. So we say taking mass, and we think of the mechanism making this possible. This is what we mean by using that term. Yes, we think, after measuring the mass of Higgs boson, of what is the temperature of this scalar field in the whole universe soon after the Big Bang, but some time had gone by, 1/100th of 1 billionth of a second. After that, the scalar field actually took place in the universe, and something amazing happened. There was the final separation of the electromagnetic interaction, which always had this endless action range, from the weak one, which was at the subnuclear distances, which changed the structure of the matter at that point in time in the universe. Thanks to this mechanism and to the specific mass of the scalar field attributed to electrons, atoms and molecules were formed, the matter which we know today. So this has plays a crucial role. I still feel excited for that. The discovery was really a crucial discovery, but the troops of knowledge, the way I call physicists and scientists, we have already archived, in a way. We put behind our shoulders emotions and feelings and excitement, and our efforts are now focused on the new questions in front of us. But there's something better now. We have another instrument. Higgs boson is so sensitive to all particles, the particles which are known and those which are not known. So it is an instrument of research in and of itself. If we produce scores of millions of those Higgs bosons. We could analyze them in detail. If we found a minute abnormality as against the theory and the standard model, that would be an indirect indication, but it would change the scenario, but this would mean a new type of physics. So we would know where to find for new states of matter and new interactions. So this is why the idea of a new accelerator arises. This aspect of knowledge. We are also interested in the machine, and we'll go back to that issue later. But when you started studying physics or taking your first steps in the academic world of research, reminding those studies in that moment, how different is this from what you could foresee at the time? Or were you expecting that in terms of the process of scientific knowledge? I think that any theorist, if theorists had to make a choice or a bet, they would have bet on the existence of Higgs bosons, because there were a number of indications pointing to that. Like a puzzle with 10,000 pieces, we put together 9,999. One is missing. We find it because it ended up under the sofa, under the couch. But finding that piece and verifying that it doesn't fit, and we must go back and start from scratch, that is possible. It would be extremely interesting, but absolutely impossible to find. But we knew that if the Higgs boson would not be there, something different replacing it would exist to make it possible the acquisition of mass and many other to acquire mass and many other phenomena. But what was surprising for those who have lived in these years is how long it took and how difficult it was. We come from a period of 30 years, during which we got used to this idea of testing hypotheses, even though they were well established. Since the standard model took root, with a couple of lines of equation, it explained what had been seen over decades, over the previous decades, and it was this evidence that the theory was correct was too strong not to be taken seriously. And this envisaged the existence of the different bosons, the W and Z, and the core top that was discovered 10 years later. We built machines to look for these things. So in this regard, the question of how can we be certain that the domain of exploration will also be a domain of discovery, that was the correct question to ask at that phase. But after closing the standard model with this discovery, we don't have those guarantees. We have a ground for exploration in front of us. And it is no longer a discovery, it is turning into a ground for exploration. As is the case in the US, there was the discovery of America, the first journey, the first trip from the Glory to Colombo, and there was the exploration of America. If we think of that, it's natural to ask this question. Is discovery more important than exploration? But without the discovery, there is no exploration. It's a discovery that is left there. Unless there had been a second trip, a third trip, that discovery would just be useless. What made the discovery great was the period of exploration. This was the same because we had the Nobel Prize and endless glory to the discoverers, and we have many years of explorations that will be extremely rich. If I understood correctly, the comparison of Higgs and Colombo is that by Cortés. We hope we're not going to have Cortés. We think your question about when you were at university, and I'm thinking of those years. that period of time. I'm talking about 72, 73, the years in which I attended Pisa University, and we discussed with our professors about particles and physics, and they told us, we keep talking about particles, but we have actually discovered everything. It's not such an intriguing, such a fascinating field. And I say this because I keep hearing people talking about that. We were actually at the threshold of what November 74 is reminded as the revolution of November, because what was discovered at the time was a new charm, a new quark. And this changed everything, actually. That discovery, which revolutionized completely, entirely, the plan, the design that was there. There were some insights, but actually the picture was completely changed. So, and this is when a new drive started, and the new direction was followed. I think this is what the new generations will experience. We don't know when or how and through which analysis. There will be a moment when a young student, either Italian or Indian or Chinese, somewhere, will develop a specific analysis, and we will find something which is not at all reconcilable with the standard model, either a new particle or a new matter state or a new interaction or a discrepancy about something that we want to measure with great accuracy, and that will lead to the collapse of what we have built so far, and that will be an important point in time. Last question before we leave. Future developments beyond the LHC, but also bordering this field. When could the new projects become operational? And in the short term, what are the difficulties that you foresee in implementing those projects? And we have said this already. But what could we expect, theoretically? The LHC still has 20 years of operation ahead. It's still very young, and over 20 years, many things could be discovered. As was always the case in the past, going to greater energies, this is our major goal. So we are thinking about new accelerators to increase energy. How and when to get there? This is a question we can answer. We will be able to answer once we have new data about LHC. LHC could unveil new phenomena, and studying those phenomena could be accelerated and made easier thanks to things that are not necessarily the greatest energy we can conceive today. So we are thinking of a very wide-ranging program for many different reasons, with instruments which are not just the accelerators, in order to be ready to cover new directions based on what we need. The challenge in the case of accelerators is quite manifest, from 27 kilometers to 100 kilometers as an average, from magnets, which are already the most sophisticated that we can have, to something which is 2 times more powerful. So the great challenge will be, we're talking about 40 years ahead in this process. The great challenge will be keeping young people, keeping the community interested. So these young people should be told, start working on this project, and you will see the outcome in 40 years. Or we can put a young person on a shuttle and sending this young person to Alpha Centauri. That is the great challenge. So it's important to keep the community involved. So see, if the LHC allowed some new discovery, that would be very helpful. In Rome, with 450 scientists coming from all over the world, we've been discussing about a dream. You must imagine a machine that does not just have dimensions of 100 kilometers of circumference, 4 times the current LHC, which is our joy and pride, but a machine with the 2 faces. One face as was the LEP and the LHC. We inject electrons and positrons, and we produce states of matter which are perfectly known, but which great precision can be studied, with great accuracy. So this is, we're talking about precision. What is the new physics? So we produce millions of Higgs bosons. We measure them accurately. We produce huge amounts of W, Z, top, and we measure them with an accuracy we never achieved, unprecedented. Any discrepancy we may find, this is new physics. This is something that will force us to break the standard model. If this brings results, or does not bring any result, we need to go to another phase, energy. We use protons, 100 kilometers. An accelerator of 100 kilometers will allow us to reach 7 times the energy of LHC. So direct research, is there any new state of matter producing abnormalities in the known phenomena, in the known parameters of the standard model? We can discover this directly. So a pronged maneuver, two-pronged. Why two-time? Because for the development of this Hadron Collider, we need to develop a technology of magnets, superconductors, which have been the lucky components of the LHC, with a density of current forcing us to use new materials, changing threads, changing technology. This requires a lot of work. It requires cooperation with business, and requires also new ideas. And since it is a huge object, we need to cut costs. We must find a way to reduce to an acceptable level the investments required. I think that the bill would be quite high, though, right? Yes, but it's worth. I want to thank you for your contributions. Again, I'd like to ask Umberto Petrin and Luca Ralli to come here to the stage.
Ringraziamo e salutiamo Umberto Petrin. Grazie.
Thank you, Umberto Petrin.
Luca Ralli che
Thank
resta
you, Luca Ralli. I think he will stay with us.
Intanto vi prego di aggiungere qua una sedia.
Could you please add one more chair? I would like to invite to the stage Sergio Bertolucci, Massimo Florio, and Antonio Zoccoli, please.
Allora, Bertolucci, Istituto Nazionale di Fisica Nucleare, Università di Bologna.
Bertolucci, INFN, former research director CERN, Antonio Zoccoli, University of Bologna, and Florio is an economist.
In mezzo pure l'abbiamo messo.
And we put him in the middle. We have to keep tabs on him.
Allora, cominciamo da Bertolucci.
So let's start from Bertolucci.
È sempre, nelle cose che ci siamo detti prima, poi in realtà abbiamo sconvolto un po' tutto.
Well,
spero che Francesca non sarà
I hope Francesca won't be too mad that we didn't follow the script. Well, we've seen a few projects. How can we predict the development of these projects when they're so long, when they're so vague from a given standpoint? But there are lots of planning up front. There are lots of intelligence of a big community that tries to carry out one of the riskiest activities for us, that is to say research, especially fundamental research, is a high-risk activity. Nothing is certain, you're never certain of the results. It's an exploration activity. And we try to minimize risk constantly. But this matches a fundamental need of our being human. That is to say, having a sort of optimism about the future. And this is something extremely important because a sound young society that has this far-reaching attitude must have this optimism about the future because it thinks about problems of sustainability, problems with the future, and it's not satisfied with what they have. Old societies are satisfied with what they have and they disappear eventually, whereas young societies think about the future, think about changing paradigm one day. That is nothing you have to take for granted. And within all this, we try to minimize risks and to maximize return. And this happens on several levels. Some levels are predictable. Some of them are unpredictable, because we know that every time we invest in a large scientific enterprise or undertaking like the LHC, there are benefits involved. And now, working with economists, we can quantify part of this. So we are not selling hot air, basically, because we are responsible, we are liable to the society, to those who pay taxes, and they support us, they pay us, they sustain us, they encourage us to go on, and we owe them something about what we do. Well, let's hand it over to Florio. As we heard, he has dealt with the socio-economic impact of projects like this, projects that are so relevant. So what conclusions can we draw from this analysis? How can we assess the exploitation of these human, financial, economic resources in the large facilities for fundamental research? They are very important works, not only physics. Well, the bad news is that these infrastructures cost money. Unit of measurement is billions of euros. For more than 20 years, I've been dealing with the socio-economic impact of traditional infrastructure. And in particular, the cost-benefit analysis was born out of a question like this. So let's assume we have a bridge, and we have to pay the cost for this bridge, and there's no toll to be paid on this bridge. So what's the society going to get if there's no toll to pay? In the case of research infrastructure, there are two different things to consider. First of all, the benefit of science. And quite often the benefit of science when the research infrastructure is planned is unknown. well, the Higgs boson was eventually discovered, but how long did it take? How long would it take to know what mankind will make out of it, practically? And that's what we're interested in. Well, our strategy over the past 3 years was that of saying, let's try not to answer impossible questions. Let's try to answer possible questions. And possible questions are, let's start with a research infrastructure like this. There are some side effects. Side effects whose scale, however, can make our ends meet, basically. And there are 3. Technological impact, educational impact, and the cultural impact. In the case of the LHC, we have calculated that given a very high cost, future benefits expected for 2025 will leave a net benefit for the society with a considerable surplus, and the likelihood of this to happen is 90%. That's interesting. You're an economist, so we are on the firm ground here. So you are an economist, so you said that a bridge, if there's no toll, what's the benefit for the society? Well, for those who build it, lots of benefits. For the society, I really don't know. Well, in this case in particular, this infrastructure, well, do really have a return for the society. There's no private profit for this. Well, there might be private profits. We have measured the fact that for businesses that have become suppliers of state-of-the-art technology, there were a number of challenges to meet, and CERN has a policy not to have patents on their inventions. So there's this outsourcing, basically. So CERN has presented businesses with something that they have sold back, so that there is financial return, and that's very clear for businesses. In regard to human capital, we expect that by 2025, 36,000 PhD and post-PhD students would have worked at the LHC. So the LHC effect on their future prospects, even economic prospects in terms of employment, in terms of making a living out of any job in the finance or in the scientific world, will last 35 more years. So the value that is created this way in terms of human capital is more or less 1/3 of the benefits that we have observed. And the last benefit, as we said, is the cultural benefit. The cultural benefit is in part direct. There are more than 100,000 people a year that go visit CERN. It's just like a big museum, basically. So the same criteria apply. What's the benefit for a person that visits a public museum, even if there's no ticket to pay? Then there are hundreds of millions of people that benefit from the cultural impact of CERN through the media, and this is measurable as well. Let's still focus on the social, economic, and cultural impact. Let's focus again on the research impact. I'm thinking of the young Italians who have worked there, they're still working there. Could you please elaborate a bit more on this? Well, I think this is a key point in what we do. I think that one of the missions of CERN is to do research, is to explore the boundaries of our knowledge, is to develop technology. But I also think that a third pillar of what CERN does is training of young people. And there are 2 main points to raise here. First of all, many PhD students go to CERN. All the PhD students that do research in the field of particle physics spend at least a year at CERN to gain some experience. And this is a training year, not only from a scientific standpoint, not only from a technology standpoint, because they learn state-of-the-art technology, and when they come back, they can apply it. In Italy, they can work for industry, and they can contribute with the heritage, but it's also a social benefit that is implied because they come to know different cultures, different mindsets, different ways of thinking, different ways of dealing with problems, and this is something that they brought back to Italy. It's a breeding ground they're creating in Italy. The second very important point to raise is the social aspect. We're going to change the microphone because there's a slight technical problem. There's a social problem now. The important thing is that this type of research contributes to raise the awareness of young people about these activities. So we have a society right now that through the television or through other media is actually proposing models that are sports champions or actresses, well, when it's good, of course. Yes, exactly. Whereas here, we are showing something that is very important, an activity that is fundamental for the growth of a country. And we make sure that young people are sensitized to this, that they become excited about this. They understand it's not something that is far from them, something that is just for an elite and then they can never access it. It's something they can contribute to. And these young people will be the starting point for a future. So part of our mission is to sensitize young people to do this job. And if we are not good at doing this, we will fail. We have done great discoveries, but there will be nobody else to go on with these discoveries in the next 20 years. So we have heard about the knock-on effect from a social, cultural standpoint, but let's focus on expectations. I don't know if the word welfare, well-being is the right word here, but from a social standpoint, rather than from an economic standpoint, we expect, hearing also what we know about these experiments that have gone through a rough patch. People thought they were dangerous, whereas once they were launched and people understood the importance of these experiments, they became a great success at a global level. So quite often, the underlying question is, what for? What's this for? Well, for those who do science, who do research, then this applies to me too. It's a question I rarely ask. But can we say something about this? Yes, definitely. We do this research because it's useful, because it's important. I'm saying this, but I'm saying also that we are doing this research because it's beautiful to do this research. We like it, we love it. So have you ever asked this question to a pianist? Why are you a pianist? Or a painter? Why are you a painter? We are artists on some levels because we are led by passion. We are led by passion, we are led by curiosity, the curiosity of finding out something nobody else has ever discovered. The curiosity of answering questions that have no answer, because that's what we're interested in. Not something we already know, but something we don't know. So the questions with no answer are guiding us. So that's the main motivation that we have. Then clearly when we do these things, we automatically find new things, and sometimes we find unexpected things. So we built the LHC to find the Higgs boson, something that theorists believed it existed, even if we didn't know where, how, what properties it might have. But many times when you're looking for something else, there are incidental discoveries. You find out something else you did not expect. And these are the breaking points that make technology and make our society progress. And this is something really exciting. Very few people have this opportunity, have this chance, but something very exciting to researchers. Would you like something about this, Bertolucci? Well, that's the history of mankind. Since man started to speak, to use language, they started also to ask questions to the neighbors, to find an interpretation of everything that surrounds them. We are following along these footsteps, and we know even if we can't anticipate how the Higgs boson is going to be used in the future, we know that in the past, and we have a consistent record in this regard, every time we understood better how the universe was working, then this thing proved useful somehow to the society. So if a society can build candles, the society will build huge candles, beautiful candles, but it will never build an electric bulb. So to move from a candle to an electric bulb, there's something in the middle. Electromagnetism. What we are carrying in our pocket is quantum mechanics, a smartphone. A transistor is not a extension of embryonic valve. If there's no quantum mechanics in between, you can't have the transistor. So the world has changed thanks to this. These are the big revolutions that change the paradigms. But in a society that is growing and improving, think about the World Wide Web. It was invented, in quotes, in 1989 at CERN. There was no new technology. There was a revolutionary idea behind, so different needs were combined using existing technology, and it changed the world. 15% of global economy takes place on the web. 20 years ago, 25 years ago, this didn't happen. So we feel an important part in the social role. We can't be alone, because we're not giving to the society. It's a society that is pushing us, pushing scientists to do what we do. And scientists take upon themselves the responsibility to give something back to the society. But it's a combination of different factors. Schools, training, the will to have a future, the will to have an appetite for curiosity and for risk. This is the message, this is the take-home, I think. The take-home of optimism that science in general is willing to give. We want to have a far-off horizon. We are not satisfied with what we have. Well, I would like to thank Bertolucci and Zoccoli. Thank you.
Il microfono, per favore.
Microphone,
Mentre
please.
Florio resta con me,
And Florio will
alzare,
stay with me.
chiamo sul palco Fabiola Giannotti, che
Fabiola
dovrebbe
Giannotti
essere da quelle parti.
should be
Vediamo
somewhere
se
here,
sta
so
sul
I would like to
microfono.
invite her to come back on
C'erano dei
stage.
problemi di orecchino per quanto
I
riguarda
think
l'aschetto.
she had
Prego, Florio.
earrings problems with the microphone.
Ah, ce n'hai uno te, benissimo. E allora siamo alla fine, evidentemente.
We are coming closer to the end. While we wait for Fabiola, I'd like to ask Florio whether, since a physicist
Visto che i fisici ascoltano malvolentieri i consigli di altri, però
don't like to listen to advice from coming from other people, but as an outsider vis-à-vis the world of physics, is there any suggestion we can give to those who actually carry out such experiments, having a fallout, having impact, which is so huge from your standpoint? So from my standpoint, and coming here, Fabiola Giannotti, I said something that I always tell my students. I teach at the State University. Through their fees, students cover 20% of the cost of their education. I tell them 80% of the costs are incurred by families who are not going to send their children to university. So the work of scientists is a bit the same. It is supported by each of us when we buy coffee, because in coffee there is VAT, so it's a small piece. In that VAT there is a microparticle, an economic microparticle of our work. So my suggestion is the following. If you manage, like you are doing tonight, to infect, in quotes, those who are going to sponsor you. This will have an amazing economic effect. Since benefits are mainly cultural, so they are measurable, and in this regard, we can say that science is a public good. The more we consume it, the more it is worth, which does not happen with apples, because the more I consume apples, the less it is worth, because I have to throw it away. So from this standpoint, dissemination is not just a matter of social responsibility, but it is the instrument that you have in order to grow social benefits of the work you do. Fabiola, can we draw our conclusions, also keeping in mind these words? And if I can add, we have been talking about technology a lot, but it is a cultural matter more. In order to conclude our discussion, drawing inspiration from what has been said, especially in this third part, I would like to point out that what we do in terms of research in physics, but also in other fields of research, I'd like to spend a few words to unify knowledge. We shouldn't put knowledge in separate boxes, science, physics, and the other sciences. I mean, knowledge is one thing, and it is the highest expression, together with art, of intelligence and of the ingenuousness of man. But in order to go back to what we were saying before, we have been focusing on three main aspects. What we do has an intrinsic value, regardless of practical applications. Because the progress of knowledge, this is a right and duty of mankind. We are thinking beings with a brain. When we came here on the earth, we tried to explore, to gain knowledge, to improve our lives through the growth of knowledge. So knowledge, research and art, these are all very precious assets for mankind. And no one wonders why we finance concerts. What are concerts for? They are important to lift up our spirits. So this, I'd like to reiterate the importance of research, of fundamental knowledge. Second point, research leads to progress directly, but for this, it takes decades, even centuries, but I'm certain that sooner or later, Higgs boson will be used for something. This very special and a tiny particle will be useful for something. There is the indirect impact. In order to discover the Higgs boson, we had to develop technologies that are benefiting mankind today, and then there are educational aspects. So we shouldn't forget that research is not just something which is abstract. It is something very tangible, very important for all of us. Thank you so much. And now I would like to ask Fernando to come. And Ferroni, where are you?
Dobbiamo scambiarci il microfono, ahimè. O è stato microfonato?
Have you got the microphone? I can't see it from here.
L'altro palmare, se c'è. Fernando, anche a te una
Fernando,
conclusiva.
some final words about our discussion. I think that being able to discuss complex subjects which are not just related to the beauty of scientific discoveries, but they actually explain its difficulty, and they show processes and pathways which are not so obvious. Because when we had to cross the desert to create the LHC, it required a specific strength, this willpower. This is not obvious for society, looking at return in terms of days. The fact that we manage here to talk not just about the charm, the fascination of discovery, but also to measure its impact. We don't have this social responsibility to warrant, to justify I'm linked to the statement of a poet who says, we were not born to be just wild, but to follow virtues and knowledge. But it would be meaningless in a mechanism that is so obviously contagious, infectious, from an idea to the actual innovation, the discovery, or the potential benefit for society, or the direct benefit also in terms of impact on medicine. I mean, it would be meaningless not to try and measure and quantify, not as a form of justification, but rather in order to be complete, to be more comprehensive, to have a set of things that making a country culturally more rich and better equipped to face the future. We are debating here in this big hall where we listen to wonderful concerts, and the fact that someone wanted to even pay some money to buy a ticket. I can say that this is impossible to explain, but we did some rehearsals before and it could work. But the fact that this happens and the fact that we can create this sort of event, this matters, and this is the right direction to go, because science, which is key for the progress of society, has to be reconnected to society itself through cultural use of science. So science can be turned into culture through these events. Otherwise, if there is fragmentation, we run the risk of wasting its value. I want to thank you all, and thanks to our audience. Thank you so much.